day of lecture on Special Theory of Relativity. So we are at the very end where we have learned quite a few things, and I hope that you have been able to see through and appreciate the completely new theory, which was quite revolutionary, which is quite revolutionary. It's challenging, it's counterintuitive, and but at the same time, you end up understanding that how the classical formalism of mechanics can be nicely generalized, okay, which takes into account the very fact that the speed of light is the maximum speed, achievable speed, and that there is a relativistic world where things are different than our usual world which we perceive. So in order to take into account the happenings there, one had to generalize the ideas of Newtonian mechanics, and that is being done first through the postulates of special theory of relativity, then putting them formally in structure through Lorentz transformations, and finally using four-vector formalism, the entire picture could be derived very easily mathematically. So today I'm going to sort of show a few more examples on applications of this four-vector formalism, and then that will be the end of it. So I'm first going to share my screen for the discussion. Let's first review what we had done yesterday and then take it from there. So, okay. So this was the main thing, that like the usual three vectors, you can define a four vector in a mathematical four-dimensional space where you have four components. And then the idea of going from one reference frame to another in special theory of relativity in mathematics, language of mathematics, it's simply transformation between two coordinate systems, and the coordinate transformation is related through these relations. The vector components, they transform through this set of relations. Now, when you consider the space-time four vector, then you get back the Lorentz transformation, relations between the space and the time coordinates. From there, we generalized it that for any four vector, these transformation rules are valid, and we ended up getting another important dynamical quantity, that is the momentum energy four vector, whose components are, the first three components are the three special momentum components, and the fourth component is the energy. So first example today I'm going to show is that the relativistic Doppler effect can be easily derived through three-four steps. So here is the thing. We have two frames once again, S and S prime. S prime, suppose, is moving in the positive x direction with a velocity v. And from S, I send a light pulse of frequency mu. And I want to calculate the frequency that is being observed or obtained by the observer in the S prime frame, which is moving away from S prime with a velocity v. So I take the momentum energy vector. Now this is a light pulse. This is photon, which is a massless particle. So we know what is its momentum. The energy of photon with frequency nu is h nu. That is known by us. I think that is what you had learned already in class 2. When and when you will study quantum mechanics, then you will, the meaning of this h will be clearer to you. But nevertheless, we know the relationship, and we know that the momentum is given as h nu by c. So since in the three-dimensional system, is completely along x direction, we have only the x component, and the y and z components are actually 0. And then we have I p by c, so the fifth component is once again I into h nu by c. Excuse me, whichever has the microphone on, I would request to turn the microphone off. So now the next thing, after defining the momentum energy vector, we write down the transformation equation. That is, I simply take this transformation equation into account, where this beta is capital V by C. Then we simply substitute the thing. You see the fourth component of the energy momentum relation, sorry, the fourth component of the general momentum energy vector and the first component of the momentum energy vector. We simply put that, and in the S prime frame, the fourth component would be H mu prime by C. So using that, we get this relationship. Okay, so that means that for an observer in this frame, the frequency will be lower than the frequency at the end. This is a result we had derived through our usual argument of light pulse being emitted and then it is being received by an observer, calculating the length, including the time dilation and all that. We didn't have to actually take this argument. It comes from simple mathematical stuff. Okay? Clear?
So can you please mute everyone? We cannot hear you very clearly.
Yeah, I think I have to do that. I'm not sure whose microphone is on.
So actually, you have an option to mute all participants.
Yeah, I wasn't doing that just because then nobody will be able to, ask a question. That's the reason. Okay. But anyway, all right, I think that person turned off the microphone. So yes, let's get back to it. What I did was I simply constructed the momentum energy vector using this relationship. Okay. And then from there, I use the transformation law for the four vectors. This transformation law, because I am interested in the momentum, the fourth component, the energy. So basically, this gives me a connection between nu prime and nu. And then just a couple of steps of algebra and this comes out. Okay. So the key point was identifying this and identifying that. That's all. You didn't have to do anything else. Is this clear?
Sir, what is I in the vector?
I is the I square is equal to -1. I taught it yesterday's class, no?
Yes, sir.
So you see, now the point is that I know where it is coming from. You are kind of perplexed that what is that imaginary thing doing? So as I say that do not consider this momentum energy 4 vector as a real thing. You cannot really connect this 4 vector to some real entity. Okay. So when it is a mathematical construct, it's a complex vector with one component being complex, and that is acceptable. All right. What we are getting out of this is it's a tool using this and making and from the fact that all the 4 vectors are Lorentz invariant, we are applying that to find out the quantities that are of physical nature. For example, this frequency of the light that is being observed by the observer in S prime. So these 4 vectors are being used as a mathematical tool to achieve what we want to achieve in a very simplified, elegant way. Okay.
Yes, sir. Understood, sir.
In the next part, when you will go to quantum mechanics, you will have even more terrifying situation where you will see that the state of the system is described by a function which is complex in nature. It is being described by a thing that got it's not represented by a real number but by a complex number. But then the question is that we always focus on the physical quantities. So physical quantities, when we calculate using that complex number, they come out to be real. So we only focus on that physical quantities. Over here also, that this is a mathematical construct. The fact is that the norm of the 4 vector should be equal to a constant. That means it is invariant across all the inertial reference frames. Okay, and so therefore with this we use that and the transformation relations between one coordinate system to another to obtain the results of which are physically meaningful, and that's what we have done. Okay.
Okay, sir.
All right. Now how we use it? This 4-vector formalism or the transformation laws. Another example I'm going to show you. In the previous tutorial, the last problem, if you remember, the last problem, A and B were part of the last problem. That we had a particle, pion, it decays into a mu1 and a neutrino. Mu1's mass were given, neutrino is massless. What are the energies of mu1 and the neutrino in pion's rest frame? Okay, mu1 and neutrino are not in rest in pion's frame, but pion's rest frame means pion has no motion there. And what is the momentum of the neutrino? I'm sure if you have done the class, the tutorial, you have gotten with these answers. Okay, so I'm simply writing down these answers. But over here, what I'm going to ask is that now assume that the pion is moving at 0.9c in the laboratory frame. So there are 2 frames. One is in which pion is at rest, that is an observer sitting on the pion, does not see pion moving, pion is at rest, whereas another observer in the lab will of course see that the pion is moving. And we consider that the pion is moving in the lab frame in the same direction as the neutrino. What are the energies and momenta of the mu1 and neutrino in the lab? So over here, we had figured out what are the energies of mu1 and neutrino in pion's rest frame. Now we are going to find out energies and momenta of the mu1 and neutrino in the laboratory frame. So basically, from one frame to another, we have to find the energy and the momentum. Okay, is the statement of the problem clear?
Yes, sir.
Okay. So now that we have these first results, we can nicely use it, very easily use it. So in the laboratory frame, once again, what we are doing is we are taking the 4th component of our energy momentum tensor. Let me go back. This is the 4th component of energy momentum tensor, and the 4th component of a 4-vector transforms across frames in this way. Okay, and I am simply going to use it. So what is the 4th component? In the prime frame, it's I E mu prime by C. It's the energy of the mu1 we are talking about. And that transforms like outside it is gamma, then I E mu by C. That is the 4th component in the unprimed frame minus I beta P mu. So once again, get back and see I beta A1. What is A1? Is the first component of the 3 momentum. Since the motion is along, so the first component of the 3 momentum is all we care about, because inherently here we have assumed that the motion is in only x direction. Okay, we are really not considering a 3-dimensional motion. So it's simplified thing. Is this clear? This relation?
Yes, sir.
Okay. So now it's simple. Mu minus beta P mu C. Now what is beta? Beta is V by C. Who's V? This, in this, whose V we are talking about? Now these 2 frames are moving with respect to one another, right? Pion's frame versus laboratory frame. So from the laboratory frame, pion is moving with a velocity 0.9c. So V is the 0.9 C. So I have plugged into that and constructed gamma using this. So I get 190.7 MeV. And then similarly, over here, you can find out the energy of the neutrino. Same thing. Only thing is that you see instead of a minus, here it is plus. Why so? Can somebody tell me? For mu1, I take this velocity to be positive, whereas in case of neutrino, I have taken it to be negative. Can somebody tell me why so?
Sir, their momentums are opposite in direction.
Exactly. Because the momentum was conserved, right? So their motions are opposite to one another. So if somebody thinks, if the muon sees that the pion is moving, or the neutrino sees that the pion is moving towards it, then the muon will see that the pion is moving away from it. So basically, what it was asked, that pion is moving with 0.9 C in the laboratory frame in the same direction as the neutrino. So we actually plugged that in and got this result. So therefore, if you are given a problem where you have been asked to find out energies in two different frames, you can easily find that. And from here now, you can calculate the energy momentum relationship also and get the momentum. Is this clear?
Yes, sir.
Okay. All right. The third example that I'm going to talk about is, you see this muon, pion, etc. The moment I start talking about this is basically why I talk about this, because these are the regions where the relativistic effects are prominent. This is happening inside a collider where the high energy particles collide and give rise to different reactions. You get new particles and you analyze. And from there, actually, the world of the elementary particles and the happenings at a very high speed in the relativistic limit, what kind of things happen, understanding of the fundamental nature of our entities, that is all done through these experiments. So that is why these are important to study. Okay, I'm now going to touch on the pair production of particles. So pair production is that you see the photons, the electromagnetic field, the quanta of electromagnetic field, the photons basically can lose energy in various ways by interacting with matter. So this pair production is one process of converting the energy of the photon to matter. Okay, so essentially what happens that a photon with a very high energy, it can create, the question is, it can create particles. Now question is that if I have a sufficiently high energy photon, can it create one electron, for example, by losing all its energy? So entire radiation energy is converted to the energy of an electron, which is a matter. Okay. Photon is a massless thing, it's radiation. Now that is not possible. It cannot create one electron, even if it gives the entire, because it would require, because electron is an electric charge, electrically charged. So electric charge is conserved in all physical processes. So from one photon to one electron, that process is forbidden because electric charge is not conserved. So in order to conserve the electric charge, what can happen is that one photon can produce a couple of particles, one with positive electric charge, electron charge, and another is the electron. So this particle with this positive electronic charge plus is known as the positron. It is the antiparticle of electron. So that the total charge of after these are created is equal to 0. So the total charge is conserved. So here is the process. So you have one photon and then it creates two different particles, E minus and E plus, electron and positron pair. Okay. So it can create a pair of particles, pair production of particles, if it has sufficient energy. But this process actually cannot occur in free space. because that wouldn't conserve the momentum. How? Let us see. So if I imagine that the process indeed occurs, then conservation of energy tells me that the photon energy h nu should be equal to the total energy of the electron plus positron systems. So in terms of the rest mass and the Lorentz factor, this is what it is. Now, at the same time, the conservation of momentum means what is the photon momentum? It is h nu by c. And what is the total momentum of this electron-positron pair? It is, v and v minus their velocities, weighted by their gamma factor multiplied with m naught. All right. So the point is that if both of them, can they be satisfied? Because that means, you see, on the left-hand side you have h nu. So that means these right-hand sides are equal to one another. Now that means that gamma plus this relation. That means this. That means this should be equal. But we know that this velocity of these particles can at most be equal to c. At most be equal to c. Now, when they are equal to c, that means they are photons. They are no longer particles. They are no longer electron or positron. So one photon producing two photons, that is not the process we are talking about. We are talking about one photon is producing two particles, matters, radiation energy is converted into matter. So V plus and V minus can never have a velocity equal to C, because then they will cease to be particles. So always this relation holds. Now when this relation holds, this equality is not possible, which tells us that this process is not possible. Did you get my point?
Yes, sir.
Sir, second, sir. I cannot hear properly, sir.
Sorry?
I cannot hear properly, sir. Please repeat once again that line.
All right. So what I'm saying is that one photon is producing a couple of particles. Now, why couple of particles? Why not one particle? Because you won't have a conservation of electric charge. Photon is a massless particle, chargeless particle. So, and if you produce an electron, it is a charged particle. So total charge is not conserved. So in order to conserve the total charge, you have to have a pair of particles. So with electron, there will be another particle called positron, which has the equal and opposite amount of charge as electron will be produced. So one photon loses its all energy into producing two particles, matters. Radiation energy gets converted into matters. Okay, both electron and positron have the same mass. So energy converted into mass. Now that's fine. Point is, what I want to illustrate is that even this process in free space is not possible. You need a medium in order for this to be to enable this. So why? Because first we write down the conservation of energy relationship. This is the conservation of energy relationship. You okay with this?
Yes, sir.
All right. Then this is the conservation of momentum relationship. You okay with that? It's simply h by c is the photon momentum, and on the right hand side is the momentum mv plus mv minus.
Please mute, sir. Someone has again opened mic.
Cannot hear properly, sir.
Who has opened the mic? I just want to figure out. Who has opened the mic? Please identify yourself. And why are you doing this? Yesterday, I actually threw away one student in the afternoon class. In spite of giving repeated warnings, maybe he had kept his microphone open and left where was wondering. So I simply threw him out. I will do the same here also. This is very annoying. Some decorum has to be maintained. All right. So you okay with the conservation of momentum relation?
Yes, sir.
All right. So you see, there is h nu on both the left sides. That means that tells me that gamma plus gamma minus into C is equal to gamma plus V plus gamma minus V minus. That is what it should be, right? Okay.
Yes, sir.
Now the problem is the following. That this also means this is only possible when both V plus and V minus is equal to C, velocity of light. Right?
Yes. Yes, sir.
Then if these two have the velocity of light, then they are no longer particles. They are actually radiations.
Yes, sir.
Right? But they are not radiations. We are trying to sort of create a process where radiation energy is completely converted to matter. I'm getting particles, material particles with real masses. So in general, this is what happens. So therefore, the conservation of energy and conservation of momentum simultaneously cannot be satisfied for this pair production. So what do? We need a medium. What do I mean by a medium? Is that we need a third particle for carrying off the excess momentum. Okay. The excess momentum has to be carried by a third particle. So there comes it. So I have a third particle at rest, a nucleus of rest mass m, and the photon goes and hits it, donates the energies, and as a result of that, the electron-positron pairs are created, and this fellow, which was at rest, is moving with a velocity v. Okay. Now this electron-positron pair, they are at rest. So understand the process. The photon goes, hits a particle with rest mass m in its rest frame, of course, and then creates electron-positron pair who are at rest, and this one moves with a velocity v. So now, how do I write the conservation of energy relation? So on the left-hand side, we have photon energy plus the rest mass energy of this particle. You see here, this m is rest mass. Please do not get confused. And on the right-hand side, what do we get? We have electron and positron who are at rest. So therefore, it's only their rest mass energy. Plus, this guy is now moving with a velocity v. So therefore, its mass is no longer its rest mass, but it's m gamma. M gamma c square is the energy. All right. Now, this nucleus are much more massive than the electron. So I am not sending the photon to hit an electron. I am sending a photon to hit a nucleus. So nucleus, we know, is much more heavier than the electrons. So therefore, this contribution of this mc square would be much larger than that of the photon energy. Okay. All right.
Yes, sir.
Are you,
Yes.
are you understanding? Okay. In fact, if you go for real numbers, for hydrogen, the lightest atom, the lightest one, this means that this h nu is this mc square is 940 mega electron volt. 940 mega electron volt is a huge energy. And now I'm talking about hydrogen atom. You go to the you go across the periodic table for the heavier atom, it's way higher. So therefore, I can safely make an assumption that this h nu is much less than mc square. So in that case, the atom will not attain relativistic speeds, and we can make a classical approximation. So the classical approximation is that this mc square gamma minus 1. So since this v is much less than c, we can write it in the following way. And to the same approximation, the conservation of momentum will give me this, so that the h nu can now be written in this form once again. Since h nu is much less than mc square, we have h h nu roughly of the order of 2 into m naught c square. What is m naught? M naught is the rest mass of the electron. So the rest mass energy of an electron is 0.51 giga electron volt. So that the threshold of pair production, the pair production will happen only if you send a photon beam with energy of the order of 1.02 giga electron. Okay.
Sir, here do we have assumed that electrons are at rest?
Sorry.
Sir, here we assume that electrons are at rest.
After electrons being produced, they are at rest. Yes. This
Okay,
fellow,
sir.
yeah. Okay. So basically, what is the role of this massive body? The role of this massive body is that it provides the medium for this excess momentum to be carried through. Because otherwise we saw that if this guy was not there, this process wouldn't have happened. So essentially, what is this result is telling us? It's telling us that if an experimentalist wants to create an electron-positron pair by a photon beam, what should be the minimum energy that the photon beam should carry? So this calculation is done through this. So in high energy experiments, before you doing the experiment, you know kind of the possible reactions, and then you can do your little calculation to find out that how much energetically my incident beam should be, so that this matters that I want to produce can be produced. So this is all done by these relativistic calculations. Now it's just not pair production of electrons. Sometimes using the particles, you create new particles. So just like from the photon, you can create a couple of electron and positron, you can also create an electron-positron pair by collision of two electrons. So here, the matter energy is converted to matter energy. So this is the reaction. You had two electrons colliding with each other, and then it creates, the two electrons remain, it creates another electron and positron pair. Okay. So you can see the charge is conserved, first of all. If the electron charge is considered to be -1, on the left it's -2, and positron charge is +1, so on the right it is -2. So the question is, what is the threshold energy for this process? What is the energy of the electrons that should be minimum requirement for creating an electron-positron pair? So the way we will do this is that using the 4 momentum energy. So we will be using the conservation of 4 momentum energy, and the trick is that we will compute the 4 momentum after collision in the center of mass frame. Because you see, the advantage of going into this 4-vector formalism is that I can work in any reference frame of my convenience I want, because we know that the 4 momentum, the norm or the magnitude of the 4 momentum is invariant. So therefore, it doesn't matter in which frame you are working. So this cartoon diagram tells you the process, that this is the first electron, this is the second electron. Consider a situation where the second electron is at rest. The first electron comes from the left with a velocity v and hits it. And then there are 2 electrons and 1 electron-positron pair are created. All right. Fine. And everyone's 4 momentum energy, 4 vector is given by this. Okay. So if I want the conservation of 4 momentum, this is the relation that should hold. Okay. Now, before collision situation, you treat in laboratory frame. In the laboratory, what do we see? We see that this guy is at rest and this guy is in motion with a velocity v. So before collision, what is P1? It is this, and the fourth component is this. Whereas for P2, there is no free momentum. This is 0. And the fourth component, E by E1, what is E2? It's only the rest mass energy, m0 c squared divided by c. So m0 c. So now, when I calculate P1 plus P2 square, this is what I will get. I will be using the energy momentum relationship of the first one. So you can do a little calculation and see that here it is for the three vectors, it is P square. So if I want to write down P1 square, what it would be? P1 square C square plus m0 square C square is equal to E square. I'm going to use that relationship, E1 square. And then this is how this comes out. So just do the calculation. Now, after the collision, I will be treat the entire system in the center of mass frame. As I said, since the 4 momentum vector is conserved, the magnitude is conserved, this is invariant from one frame to another frame. So I'm free to choose in any frame I want. The before collision, I treat in lab frame. After collision, I'm treating in center of mass frame because that's convenient for me. So this is, you can sort of think of this is happening in the center of mass frame. So when we write this, these are the 4 components. Now tell me what will happen to this in the center of mass frame. The magnitude of this, the total 3 momentum. Anyone? What happens to the 3 momentum?
Sir, it remains, it will be 0.
It will be 0, exactly. That's what I am going to use. So therefore, P3, P4, P5, P6, these vectors, this gives you 0. So I'm only end up getting this component and this gives me the result. So now the momentum is conserved, I equate these two, and from there, I can find out the threshold will be 3.57 mega. So you see, I had dealt with 6 particles, but how easily I could calculate this thing. It's just one slide calculation. Because the trick was, using the 4 vector, was that I could treat it in center of mass frame. Make it convenient for myself. If we try to treat it in laboratory frame,
3 momentum, sir, in the total 3 momentum in the lab frame was 0.
no.
So then how come the 3 momentum in center mass frame is 0?
Wait. Total 3 momentum, if I had treated, forget 4 momentum, if I had treated 3 momentum alone, right? Can I do it before collision in lab frame and after collision in center of mass frame?
No, sir.
No, sir. No, for 3 momentum
we can't, right? But here we are doing 4 momentum. So the way you do problems up to 3 momentum was before collision, if you are treating in lab frame, after collision, you have to treat in lab frame, right? Yes or no?
Yes, sir.
Or before collision, if you treat in, or after collision, if you want to treat in center of mass frame, before collision, you have to treat in center of mass frame. Yes or no?
Yes, sir.
Right. But here we are dealing with 4 momentum. So for 4 momentum, there is absolutely no compulsion that I have to use same frame before collision and after collision, because the 4 momentum value, the length of the 4 momentum, the magnitude of the 4 momentum, which is given by this, is same in all frames. Okay.
Yes, sir. Yes, sir.
Right? So that is why I can choose, pick and choose the frame in which I want to work at my will. Before collision, I did it in lab frame. If you say, oh, what is the 4 momentum in CM frame before collision? It's the same. It will be the same, right? because that's what the four momentums are. So after collision, I'm treating it in CM frame. If I had treated it in lab frame, it would have been the same, the four momentum. Now, what is the advantage of treating the after collision phenomena in CM frame is that I know that in center of mass frame, 3 momentum is 0.
Okay, sir. Okay.
I made the
Thank you,
3
sir.
momentum 0, made my calculation simpler, and I am done. That's the difference between the 3 momentum and the 4 momentum. Okay? So that's the little trick
Yes, sir.
one has to use in order to work out these problems. So my motivation of showing you this problem was that on one hand, I wanted to get you get this information to you that in the world of high energy experiments, these are the processes that one can simulate using relativistic special theory of relativistic treatment. And second thing is that the trick of or the advantage of using the 4 momentum vector relationship or the 4 vector in general is that it simplifies my calculation to a big extent. For example, from this problem itself, you can figure out that if you had only focused on the 3 momentum, this would not have been possible at all. First of all, you cannot treat the before collision and after collision in different frames. And second thing is, if you try to express things in center of mass frame, for example, I mean, calculations would have been extremely messy. Okay. All right. So that's all for our lecture part. Now we have some time and I am ready to take some questions. Any question in general? Course formally is over and we can have a discussion.